Good morning. My name is Diego Rivas. I will go to present you our theme. It's named on the role of the microstructural properties on the mechanical anisotropy of API X46 steel. As we know, low carbon steel have a wide application fields, in particular for pipelines. It is well known that the variation of the mechanical properties related to the directionality and orientation of the microstructure is present in the pipelines. Also, along with the steel manufacturing affects the microstructure features. Things like inclusion distribution, microstructural anisotropy, like particle band alignment, and crystallography texture could affect that mechanical behavior. Even though this well-known phenomenon, there is very little data about how those characteristics affect the mechanical properties, like the degree of banding. For this reason, the objective of this work is to determine quantitatively the influence of the microstructure orientation on the anisotropy of the mechanical property. Well, we start with that material correspond to API X46. We have the composition of our material and the reference composition. We took those surfaces to start to or related with the construction of fabrication of the pipeline, and we take the longitudinal and circumferential sections and were analyzed by optical microscopy and electron beam scattering diffraction. Taking that reference, we made the tensile specimens oriented by the same directions, and the sharpening back tests were made in the same with the same characteristics. The fractal hotness was calculated by the ASM equation, and then was compared with the microstructural characteristics. Those are our results. As you can see, the grain size and the inclusion content and phase are very close for the longitudinal direction and circumferential direction. The change that we have, we can see in the microstructural characterization, that is the banding, degree of banding of perlite and orientation of the grains. And we can see a slight, a little banding of the perlite in that section that corresponds to the longitudinal direction, and this is the circumferential direction. Then we made a textural analysis to determine the density of the orientation of the crystallographic orientation of the steel, and we determined the variation in percent of the planes presented in longitudinal and circumferential direction. We have to the mesotexture analysis, and we have to difference between the long angle grain boundaries and high angle grain boundaries in the longitudinal direction and circumferential direction. It's around, how you can see, 20% of difference between two directions. And we calculate the difference in tensile stress, and we have that both directions is in the limit of correspond with the specification, but there are difference between two directions evaluated. The sharpening properties show us a difference in the two directions, and the fracture resistance show us to that difference around 18% of difference between those directions. And finally, we use a coefficient of relative variation that establish that there are a difference between the mechanical characteristics and the microstructural characteristics. And to that point, we have the next conclusions. A low carbon steel used in this study showed an isotropic behavior with large fracture resistance in the Z direction in comparison with all directions, having a mean difference around 18%. The tensile strength property showed the same behavior and fracture resistance with larger values of yield strength and UTS strength in the Z orientation than the L orientation, but with different amount of percentage of difference. The related variation coefficient shows that the degree of anisotropy of the fracture resistance and tensile strength of this steel is determined by the amount of grains oriented in those planes, 101, and the microstructural banding parameters show an inverse relationship to the fracture resistance and tensile strength properties. Since the higher banding degree, the lower mechanical properties. Okay. Thank you for your attention.
Thank you.